Welcome back to Caie Math Homework. I'm very pleased to come your way once again with a past paper review, this time around on Mechanics 1. All the M1 questions come with something very peculiar. Usually the very last questions, 5 and 6, come with some twist that I will entreat you to stay through so that we discuss these and get you prepared for your M1 paper. Let's get right into it with very first question. A lorry of mass 16,000 kilograms is traveling along a straight horizontal road. The engine, the lorry is working at a constant power. If the work done by driving force in 10 seconds is 750,000 joules, we want to find the power of the engine. So power is the rate at which work is done, right? So if you have the work done by the driving force, that's power be the work done divided by how long it took to do that work. So in this case, so the power the engine is 75 kilowatts. The B part of this question give us the value of the resistive force acting on the car. Our work here is to calculate the acceleration of the car at a point in time where its speed is 25 meters per second. So acceleration has everything to do with the net force acting on this body. So it will be good we calculate the value of the driving force with the power we have and then use that to determine what the net force would be. So let's start by calculating the driving force. We know that power is driving force times velocity. So if we should rewrite this equation and make driving force the subject, be able to find the value of the driving force given the power and the velocity of the particle. The net force acting on this car in the direction of motion, which is giving us, that gives us the value of the acceleration of the car to be. Now this 0.0375 meters per second is the exact value of the acceleration, or and it's also correct to 3 significant figures. So we'll just leave it as it is and move on to question 2. Let's look at question 2. Particle is initial at rest and accelerates at 2 meters per second. So we want to find the time it takes for to travel a distance of 1 meters where it starts. Given that tan of alpha is 3/4, let's see how that helps us to calculate sine and cosine alpha. Now, given that so using s equals ut plus alpha ac squared, can calculate the value of the time it takes particle to travel a distance of 1 just from its starting point. The B part of this question wants us to calculate the value of the coefficient of friction between P and the floor. So now let's determine the normal force acting on P by the floor. Now I want to calculate the value of the coefficient of friction between the particle and the floor. We want to start with knowing the net force acting in the direction of motion, giving us so the net force in the direction of motion is going to be given as 3 times cosine of alpha, which is the horizontal component of the upward force applied minus the friction. So that allows us to calculate F as 1.6 Newton. Now vertically, the body is not moving, and hence the net force should be equal to 0, implying that now since the body is in motion, the friction experience is going to be the peak value, which is given as F is equal to mu r, implying that mu should be equal to. Now let's look at question 3. We have this cross section of a path taken by a particle from A through B to C, and being given information about various points along this path. Now work is to calculate the value of h, given that at B the particle speed is 3 meters per second. If you set it at A at 5 meters per second. So let's see how that goes. You need to realize that the body at A has some amount of kinetic energy which reduces. So then there should be some kind of conversion of that kinetic energy into some other form that we need to take into account, and that will help us to calculate the value of h. So let's see what the change in kinetic energy would be from the point A to the point B. In calculating change, we try to find the final value and then subtract the initial value from that final value. That's how come we get change. And if that change is positive, that means it's an increase, and if that change is negative, that means it's a decrease. In this case, if the body started with a speed of 5 meters per second and ends up with 3 meters per second, then there's a decline in the kinetic energy, and that's how come our change in Ke from A to B is a negative number, negative 1.6. Now let's look at the change in gravitational potential energy between these 2 points. Now this is positive because the body is moving up, and as you do so, you gain gravitational potential energy. Now, since there are no external forces, there's no resistance to the motion of the particle from A to B, we can use the conservation of energy principle, which states that so the value of h is 0.8 meters based on the information given to us. Now, the second part of this question indicates that there's actually a resistive force in the motion from A to B, and the work done against this resistive force is 3.1 joule, and we want to use this new information to calculate what the speed would be as the particle reaches C. You can use any two of the 3 points to calculate the changes in energy and analyze the speed at C. However, we have a lot of information about A, and we are trying to figure out what's happening at C, so it will be a good idea to calculate the change in energies between A and C and move on with that. Furthermore, we have the 3.1 joule of energy is actually work done against resistance moving from A all the way to C. So then let's check and see what happens. This is a change in kinetic energy from the point A to the point C. Let's look at the change in gravitational potential energy. Now let's look at the work done in context. So first of all, before that, the change in GPA here is negative because if you consider the motion from A to C, the net displacement is 0.5 meters downward from A. So that's how come the change in GPE is a negative number, because the body is moving from a higher potential to a position with a lower potential, which is C. So now let's look at the work done. The work done against the force, because that force is not in the direction of motion, work done against that force would be taken as a negative number. If it is a force that is in the direction of motion, would have reported the work done by that force as a positive number in our energy equation. So just note that. Now let's see the work energy principle in calculating the speed at C given the information that we have. So note that V squared is given as 4, and we are looking for the value of speed, and speed is just the magnitude of the velocity. We're going to report that as the positive square root of 4, which is 2 meters per second. That brings us to the end of question 3. What I want you to note here is that the change in kinetic energy would be a positive value if the body ends up with a higher value of speed than it started with for the 2 points you are considering. And change GPE is positive if the body moves from a lower level to a higher level, and negative otherwise. And work done in the work energy equation is positive if the force involved is acting in the direction of motion, and work done will be negative or considered negative if the force involved is acting against the direction of motion. So that's just something you need to know. So the general expression looks like this. So you realize that whatever change in energy takes place, the sum of all those should be equal to the work done by any external force involved, whether or not they are for the motion or against the motion. Question 4 is in two parts. A body travels along a straight road with a constant acceleration. So this statement allows us to use all or any of the equations of constant acceleration. We have v equals u plus at, v squared equals u squared plus 2as, and so on and so forth. So let me just list the equations here for us to see how I'm going to use them. There's a fifth equation I'd like to introduce here for those of you who are yet to see it. That is s equals bt minus half at squared. Now let's see how this equation works. First of all, let's rewrite this very first equation as, let's substitute this into this very equation and then see what we get. This second equation looks very similar to what we have up here, which is the usual thing, s equals ut plus half at squared, except that instead of making use of the initial velocity, to calculate the distance traveled with the given time and the given acceleration, rather using the final velocity, the given time, the same information about the particle to determine the distance traveled. So those of you who are yet or who have seen this for the first time, it is possible to have S equals Vt minus half At squared. In addition to all you know already, S equals Ut plus half At squared. And let's see how this helps us. There are so many ways around this question, but the most direct and the easiest is what I want to introduce. So just stick with me as we go through that. So the particle passes through the points A, B, and C in that order, and it takes 2 seconds for the particle to move between each interval from A to B, then from B to C. We've also been told that the speed at B, I'm going to call that VB, is 4.5 meters per second. And we know that the distance AB is 4/5 times the distance BC. That's some information about this particle that we need to consider. Great. So with what we have in the journey from A to B, the 4.5 here is actually the final velocity. So we can say that so this is making use of this equation, S equals Vt minus half At squared. So the 4.5 here is the final velocity considering the motion from A to B. And that's how come the sign in here is negative as it should be. And of course, the 2 here is the time it takes to travel through section from A to B or from B to C. Now let's simplify this and continue. Now for the distance BC, the 4.5 here is the initial velocity for that motion. So then we can say BC is equal to with this information, we know that SBC is 9 plus 2A. And we are taking A, of course, to be that constant acceleration that the body has in moving from A through B to C. So now let's look at the given statement regarding the displacement or the distance AB, the distance BC. So using the statement SAB, so SAB being this equals 4/5 times SBC, which is that we wrote this linear equation involving just A and solve that for the value of A, which is 0.5 meters per second squared. Now let's use this value of the acceleration to calculate the distance of AC. And of course, the distance AC is just the sum of the distance AB, the distance BC. And even without knowing what the value of the acceleration is, we could have calculated that distance, because adding the distance BC to the distance AB should give us the distance AC. That's as simple as. Of course, it happened this easily because of the approach we took. In a different context, we may have expressions involving displacement that will need the value of the acceleration that we have calculated to arrive at whatever this is. But in any case, so long as you use any of these equations appropriately with the given information, and you do the algebra right, you're likely to get A to be 0.5 meters per second squared, and the distance AB to be 18 meters as required. Now for this next question that involves forces, let's resolve all the forces into their horizontal and vertical components, and that will let us know um, what the value of F be given alpha to be 60 as required for the A part. So for the first column, I'm going to have force. For the next column, I'm going to have the X components. So if you realize, you see that I have negative uh, indicated in front of some of the components, implying that they are acting in a direction opposite to what I consider as positive. For instance, I took this positive direction, and that's how come the 6 Newton force acting vertically downwards has a negative y component. Now, from the statement given here, if the net force uh, of these four forces is acting in the direction of the 3 Newton force, we're going to calculate the value of F. Find that the net force has no component along y, and that here means that now we couldn't have used the x component directly because all we know is that the net force acting on this particle has a component in that direction. As to what the value is in that direction, we don't know. And that's how come it's good for us to use what we are sure of, which is the fact that the component in the y direction is 0. So the value is 0. We have one equation involving just one variable, which is f. We solve that for the value of f. Now we're given that the particle is in equilibrium. In that case, the net force acting is 0 in every direction. So we want to find the value of f and what alpha should be for that to happen. And that will mean that the following equations hold. We can rewrite this as, and then and from these two equations, we can divide equation 1 by 2 to have just one variable and one equation. Non-linear, but we can find the value of alpha from dividing equation 1 by 2 to have. This is 83.4 degrees, correct to one decimal place. In order not to use this approximation for our next thing, we ideal we square equation 1 and equation 2 and add those two equations to find the value of f. So f in that case will be given as so this is 4.03 Newton, correct to 3 significant figures. And that brings us to the end of this particular question. Remember, you could have substituted the exact value of alpha into any of these two equations to find f. The reason I don't recommend this is in case you got the value of alpha wrong for some algebraic slip or some error with your calculations, that's going to lead to a wrong value of f. So it would be ideal to square equation 1 and 2, and the sum of the left hand side will give you f squared sine squared alpha plus f squared cos squared alpha, which will lead to just f squared, and that should be equal to the square of whatever is on the other side, and that leads us to f being the square root of the sum of the squares of those two expressions, giving us 4.0 corrected theory significant. Good. So let's look at question 6. As you get closer to the end of the paper, you need to pay rapt attention to the questions and the details that are given, because it gets trickier as you approach question 7. So question 6, I expect that there are certain things that they are looking out for that you need to be very vigilant in order to score everything out of. So let's start. I just want to point out that you should realize that if you have a system in equilibrium of connected bodies moving, if the connection is still intact, that means that the magnitude of the displacement of one body should be the same as the magnitude of the displacement of the other body. Imagine you have a rope tied around you, or even the situation we are describing here, that a driverless vehicle with no passengers are being tested, and they have a car that has a mass of 1600 kilograms towing a trailer of mass 700 kilograms along that straight horizontal track. Now, if there's a tow bar, a rigid tow bar in between them, then note that when the car moves forward 1 meter, the trailer has to follow by the same amount of displacement. And if the car moves forward or backward at a speed of 2 meters per second, for instance, the trailer has to follow with that same speed. And if the car should accelerate, the trailer has to also accelerate by the same magnitude. So you need to calculate the magnitude of the force in the tow bar. Another thing I want you to pay attention to is this. The magnitude of the force within a tow bar or a string or a spring would have a fixed value, given that there is not stretching. The length of that string or spring or tow bar has not increased or decreased. Another thing you should note is this. There is a bar, so I'm just going to draw the bar for now. And for now, I don't care about the weight yet. We'll get back to what the weight should be. Now let's take the trailer. The trailer can only move forward as a result of the connection to the car. So I'm going to call this, even though it does a tow bar, but if the car should move forward, the trailer has to follow. And that happens because of the connection to the car through the tow bar. And giving the resistance to the motion of the trailer as 200 N. Now, when you apply a braking force, of course, that means the engine should stop producing a driving force for the car to want to slow down. So that braking force acts against the direction of motion, and so try to slow down the car this way. Now, when that happens, picture yourself as the car moving forward, and then you apply a brake. The brake is applied to the car and not the trailer. So if you were the car, you'll be slowing down, alright, but then you feel a push on you from behind, which is from the trailer. So the force in the tow bar is going to be acting this way on the car. That's what happens. On the other hand, imagine you at the trailer, there's a car you are connected to that used to be moving very fast and now starts to slow down. You're going to be running into that, and you're going to be experiencing a pushback. So this is not correct. This is supposed to be acting this way. Same magnitude, but for the trailer, there's a pushback. The car, there's a push forward, and it's that same force in the tow bar. pushing the car forward, pushing the trailer backward. Good. Now, if the deceleration is 12 meters per second, that just implies here that the rate of slowing down is happening at a rate of 12 meters per second every second. In other words, the net force acting on whether the trailer or the car is acting in direction opposite to where they are both moving and has a magnitude of 12 meters per second multiplied by their respective masses. So let's look at the trailer. The trailer we've explained that would moving forward all right, but experiencing the force in the tow bar, I'm going to call that Ft, and also the resistance to the motion of the trailer, which is 200 Newton. The net force in the direction of motion, which is the mass of the trailer, is 700 kilograms times the acceleration that it will have. Because that the body started moving in this direction, we are taking that as positive. And if there's a deceleration, then the body will now have 700 times negative 12 as a net force acting in the direction of motion. And that should be equal to. So the magnitude of the force acting in the tow bar is 8,200 Newton. 8,200 Newton. Now let's consider the car and calculate the value of the braking force. Now, if the car at the instant where the brakes are applied has a speed of 22 meters per second and is 17.5 meters away from a stationary van, which is directly in front of it, I want to show that the car hits the van at a speed of 8 meters per second. Now this is like very straightforward. So we have the acceleration of the car given to us. We have the distance that needs to be traveled in order for us to hit the car. That's the initial speed at the moment for that subsequent motion. Great. So that's the value of the speed of the car when it hits the van or when it travels a distance of 17.5 meters forward, starting with a rate of 22 meters per second. We are told that after the collision, the van starts to move at a speed of 5 meters per second, and the car and the trailer continue moving in the same direction with a speed of 2 meters per second. And with that information, we want to calculate the speed of the van. So we began with something involving motion, and then later on a little bit of momentum has showed up here, but that's fine. Let's see how that goes. Now, looking at the conservation of momentum when bodies collide, we can write the following. With the collision, I'm going to take M1 as the mass of the trailer and the car together, but they were all moving with the same speed. So I'm I'm going to put the two together as one and get its momentum. And I'm going to take the mass m2 to be the mass of the van. So maybe you could have written that as mv if you want to. And initially, of course, that van was at rest. And after the impact, but just before the impact, the car and the trailer were moving at a speed of 8 meters per second. And right after, they both started moving with a speed of 2 meters per second. Let's substitute into this equation to determine what the mass of the van should be. So the mass of the van is 2760 kilograms. And that brings us to the end of question 6. So if a particle that moves in a straight line through the point O, and its displacement from O at any time is given by two functions, one defined for t less than 6 and the other defined for t greater than or equal to 6. We want to find the value of t when this particle is instantaneously at rest during the first 6 seconds of its motion. And of course, being at rest has everything to do with the velocity function having a zero value at a particular time. So let's calculate that time. Velocity function, of course, is a differential of the displacement or position function, which in this case has a value of. If this is equal to 0, then conclude that. So this is a time, 1.5 seconds, it takes for this particle to come to an instantaneous rest. And of course, it is within the first 6 seconds. Now we're told that at t equals 6, the particle hits a barrier at a point P and rebounds. So in hitting the barrier, it's like just arriving at P. And for you to arrive at P, we need to have the first equation. So the velocity with which the particle arrives at P would have everything to do with this displacement function, which we already used as a way of arriving at our velocity function for the first 6 seconds, which in this case is that. So at t equals 6, the velocity of this particle is going to be. The next thing we want to do is look at the speed that the particle rebounds with. And in the rebound, we are going to be exceeding or looking at the other end of t. And that's how come the second equation comes to mind. So let me just rewrite that second equation as. And this gives us a velocity profile that looks like. At t equals 6 seconds, the rebound velocity is going to be. This is negative 3.67 meters. The exact value velocity is that negative 11 over specific. So the final part of this question wants us to calculate the total distance traveled by the particle in the first 10 seconds of its motion. Now we need to be very, very careful. If at some point the particle came to a rest, then there's a likelihood that there's a change in direction happening. So we need to be very careful in calculating distance traveled, but this is not displacement. So I will entreat you to calculate the distance traveled the first 1.5 seconds where the particle came to a rest and change direction. And then for the second part, of course, we can just move on from there and just integrate this function and evaluate the distance traveled. So I would write the distance traveled as so in the first 1.5 seconds, the particle was actually moving such that it had a negative displacement, and that value is negative 2.25 meters as shown. So the distance traveled, we're just going to take the magnitude of that as 2.25 meters. So the first 1.5 seconds, the distance traveled is 2.25 meters. Now for the remaining 4.5 seconds, and for the last 4 seconds, so again this particle had a negative displacement, but the distance traveled, we are going to call that the absolute value of this negative number. So total distance traveled in the first 10 seconds, total distance traveled in the first 10 seconds is going to be given as it is crucial to work out the points where the velocity of a particle becomes zero. Those are likely times where there's a change in direction. So you need to consider these in calculating distance traveled, so that even though the displacement might be negative, the absolute value will give the distance traveled, and total distance will be the sum of the positive values of these displacements in the end.